Welcome. Today, we're delving into a catastrophic event that shook the world, the December 22, 2018, flank collapse of Anak Krakatau volcano in Indonesia, and the deadly tsunami that followed. This event has been under intense scientific study, offering crucial geophysical insights into how such disasters unfold and how we might better prepare for them. What's truly revealing is that this collapse wasn't entirely sudden. Using satellite radar data, a technique called INSAR, scientists discovered that Anak Krakatau's southwestern flank had been slowly slipping for over a decade, from 2006 to 2018. We're talking about a cumulative slip of around 15 meters. This silent slippage saw periods of speeding up and slowing down, but notably accelerated in the months right before the collapse. An eruptive phase that began in June 2018, adding more weight to the southern slopes, likely pushed the already unstable flank over the edge. In the year before the collapse, the flank was moving towards the ocean at about 4 millimeters per month, a rate that jumped to 10 millimeters per month once the eruptions intensified. This highlights the power of remote sensing tools like INSAR for monitoring volcanoes, especially where ground instruments are hard to maintain. Then came that fateful day. A significant portion of Anak Krakatau's cone, less than 0.24 cubic kilometers of rock and debris, predominantly from that shaky southwestern flank, plunged into the sea. This submarine landslide was the direct trigger for the tsunami. Post-event mapping using bathymetric and seismic data showed a jumbled, blocky seabed southwest of the volcano, with debris blocks up to 70 meters thick. The landslide spread out over about 7 square kilometers underwater. The tsunami generated was devastating. Run-up heights reached up to 13.5 meters in coastal areas of Java and Sumatra, causing over 430 fatalities and injuring thousands. The scale of this tsunami was actually larger than some models predicted for a landslide of this volume. This suggests complexities in how these tsunamis are generated and travel, especially with the surrounding Krakatau Islands influencing wave patterns. In fact, run-ups on these nearby islands might have been as high as 40 to 50 meters. Interestingly, the volcano's eruptive style changed dramatically after the collapse. It switched from explosive strombolian activity to Surtsian eruptions, which happen when magma interacts directly with seawater. This shift was detectable through seismoacoustic measurements. Some studies also indicate intense infrasound signals for about 8 hours before the main collapse, alongside minor seismic tremors from smaller mass movements. So, what are the lessons from Anak Krakatau? A huge one is the urgent need for tsunami warning systems that can detect tsunamis not caused by earthquakes, but by events like volcanic collapses. The existing systems at the time were geared towards earthquake-triggered tsunamis, which left coastal communities tragically vulnerable. Geophysical research is now intensely focused on improving monitoring by combining satellite data with ground-based seismic and acoustic methods to catch subtle signs of instability. Scientists are developing more accurate models for landslide-generated tsunamis, factoring in complex seafloor shapes and island interactions. There's also a push for real-time forecasting using pre-computed scenarios and continued investigation into the precise mechanics of how these collapses trigger such devastating waves. The Anak Krakatau event serves as a stark reminder of the destructive power of volcanic flank collapses and the critical role of ongoing research in safeguarding coastal communities worldwide. Thank you for listening.